Okay. So first thing I want to address is the possibility that you guys might need more practice with the algebra. It seemed like some people had a bit of concern about that, and with graphing of functions. So I'll say that for like some of the algebraic manipulations, this book is really good to use. So let me just share my screen instead. That way we can jump to this document. So this website, it's a free book, but it's good in that the problems that it has are quite they're challenging, and that makes them useful for like practicing with. So for example, what should I exponent properties? Yeah. Okay, so yeah, you can see then that there's these kinds of things. So this is just reviewing that you actually remember your exponent properties, which comes into play in some places. And then there's also fractions, doing some fractions. I think maybe this one. Everyone is seeing my screen, right?
Yes.
This is not what I was looking for. I was looking for complex fractions. Complex, there we go. Complex fractions. Yeah, so these kinds of things really show up in the limit calculations that we do when we start creating these limits that come from the derivative or the difference quotient. I have a message in here. Okay. All right. And even more useful is you can also double check, because it actually gives you solutions, so you can double check your work. It actually, I think, does just does the odds. Yeah, you can double check your work that way. Another thing is the unit circle. So I did sort of just say, like, for example, that you should just know that like sine of pi over 3 or something is root 3 over 2. But basically, what we usually teach you is to remember this table of data. So it's like this is the whole unit circle. And I guess, oh, this is actually not the right link. This is the full link, but you can, I'll send it through chat to everybody. And then you can, I don't know, save the PDF somewhere. I'd rather not actually modify the document, so don't do that. Actually, it doesn't matter. I can always undo it. But yeah, so this is the whole unit circle. But usually when you're taught it, you're not taught like the various structures and properties that are within it. So I basically wrote a few things down that sort of showcase it. The first is this. So you should know the trig functions at all the special angles that you would in the first quadrant. And you can see that there's like patterns here. Like going in this row, you've got this ascending numerator. Then this is just the first row, but in reverse. And then this row, I think of it as multiplying by root 3. So if I multiply this by root 3, I get to this. Multiply this by root 3, I get to this. And but you should also think of tangent as being sine over cosine. So then you can also just divide the columns. And this image, along with this table, this is just so that if you ever encounter an angle that is not in the first quadrant, right? These are just first quadrant specific. If you have an angle that's over in the second, third, or fourth, then you can figure out the value by actually using what the reference angle is, and also the sign that the function should take in that quadrant. So when I actually do these kinds of trig evaluations, I sort of use these three tables together. Another useful fact to know is that cosine is projection of the point on the unit circle to the x-axis. Sine is projection onto the y-axis. And that's one way that you can figure out these two columns, right? So these ones are pretty easy because they actually show up in triangles. But these two, you can think of it either as being the graphic, the plot of the sine function and the cosine function, or you can think of them as being you're at this point here, or you're at this point there. And then you just remember that cosine is the x coordinate, sine is the y coordinate, and then you just read them off. Okay, so I think that's all I wanted to say in terms of reviewing these two kinds of things. Any questions before we get started? I'm going to correct the mistakes I made on number 3 and 9, and then we'll do the rest of the homework set. No? Everyone's happy with that? All right. So hopefully you thought about what I did here, and you will have realized the inaccuracy here, which is that what we actually find from this, right? So what we did in this part here is we figured out when is cosine of some angle equal to 0. It's pi over 2 and 3 pi over 2. And then you extend that by looping around the unit circle as many times as you want. That introduces this plus 2 pi k. The problem is that that doesn't mean that you solve this equation and then you end up getting this and then you tack on the plus 2 pi k. That's not true. Instead, what I have to do is, I don't know if this eraser is not the right one. Okay, so this here is right so far, but what we really have is this. Okay, and this is what we solve, and this is what we will get. This is how we will get the full set of solutions. So I'll have to subtract pi and then divide by 3. So subtracting pi, I get negative pi over 2. And then we have a plus 2 pi k still. And then we wrap a divide by 3 around everything. And for the other set, we subtract and we also divide. This will give us pi over 2 plus 2 pi k. All right. Now, we can say a few more things about this because these answers don't look very nice, and we can actually simplify this quite a lot, in fact. So the first thing that comes to mind is we could actually we could distribute this 3 in to both of these. That makes it look a little bit better. Trying to figure out how I want to explain this. Well, I think what I want to do is I want to actually start listing out some of the values that you'll get if you plug in different values for pi. So you can get minus pi over 6 by plugging in k equals 0. If you plug 1, you'll get 3 pi over 6. I'm going to actually leave it unreduced, and then 7 pi over 6. And you can hopefully see a pattern with that. With the other set, if you plug in, you can get pi over 6, 5 pi over 6, and 9 pi over 6. All of this is because, in fact, what happens is that these two families can be combined into one family. This happens because the angle here is the same as the angle here. Okay, so instead of wrapping a full revolution around to go from this point back to itself, we could rotate by half by pi, and that would go to this point. By pi again will go to this point. So we didn't actually need to split this into two things. If we were a bit cleverer, we could have seen that immediately, and instead used pi over 2 plus pi k. This could have been the family that we started with, and then we would only be dealing with one equation. But now I'm sort of trying to combine it from this step onwards. So when we combine these two, notice that you always have pi over 6, and you have the odd numbers on top. Is it all odd numbers? 1, 3, 5, 7, 9, yeah. So you can write this as 2k plus 1 pi over 6. 2k plus 1 is just the standard mathematical way of writing an odd number. So where k is an integer. So this is the right answer. All right, so this is the full set of solutions to this equation. Does that make sense? Any questions? And the next one we need to do very silly mistakes with graphing a parabola. So apparently I have to think a little bit just to graph a parabola correctly. So the normal thing that you do is when you go over by 1, you go down by 1, or you go up. But in this case, the parabola opens downward, so we go down by 1. Then when you go over 2, you're supposed to go down by 4. I instead went down by 3. I don't know why. 2, 3, 4. So then when we go down by 4, we end up hitting this point. And 1, 2, 3, 4, we end up hitting this point, except this is actually an open circle. So and then can connect the two. This is now the correct graph, I think. Yep. Good. And so now we can correct these limits that we figured out by just reading from the graph. So this one, 2 from the right, the actual value is supposed to be 1. From the left, it's 0. This still does not exist because these two are not equal to each other. -2 doesn't exist, again, because it doesn't, the function doesn't have it defined in its domain. And this one, well, there was no problem with that. I think there was one here, yes. So now that that point has changed, approaching from the left-hand side, we end up getting 1. And so both of these are 1, which means that, in fact, this two-side limit does exist now. And it takes on the same value. And okay, this also changes. Plugging in at 2, we'd get 1, and then you've got 5. All right, so that fixes all the mistakes. Now for the material that I guess you were lectured on yesterday. So now we start to, for this problem, we start to use like the limit rules. So the shortcut that you can think of is, have you guys learned continuity yet? Did you guys learn continuity? Is it on the slides? I have to find it otherwise.
I don't remember talking about it.
I don't think so.
Okay. Okay. So continuity is like a technical shortcut. So when you look at this thing, you kind of know like you should just plug it in, right? But we tell you very technically that like a limit by definition is something where you don't actually plug in. You're not allowed to plug 3 into the function. But because the functions, we kind of assume all these functions are continuous, that the definition of the continuity says that taking the limit and evaluating are going to give you the same number, or the same result. So that's like a way to shortcut. But if you haven't covered that yet, you'll cover it very soon. I guess for this, like you're supposed to show it formally using all those limit properties. So the first thing is that the limit will split over the addition, and it will you'll be able to pull a 2 out of it. So I can combine the 2 steps, and I'll get this plus 2 times limit x approaches 3 g of x, right? All I did was I applied 2 different limit laws. And then the next thing is, well, we know what these 2 limits actually are. So then we have 7 plus 2 times 9, 7 plus 18, which is 25. For this one, it's pretty much the same. The limit, there's a limit law that says it will split over the division, and then it will again split over the multiplication, and it will split over the addition. So you could write like 4 limits. Maybe I'll do that. Limit x goes to 3 f of x times limit x goes to 3 g of x over limit. So this is the one that's like kind of stupid to write down, but technically that's what you would end up writing. Okay. So like applying the limit laws just blindly, you split it, you push it through all the mathematical operations, addition, subtraction, multiplication, division. And now we have this number, limit of a constant function is just going to be that constant value. And then limit of x is just going to be whatever that value approaches. So we get 7 here, 9, 2 plus 3. And that's 63 over 5. Now for this one, you can push it through the square root function. So there's a limit law that says if you have a function raised to some power, you can push it through that power operation. And so this is going to, when you push it through everything, limit f of x approaches 3 plus limit x approaches 3 g of x. So you get that. And well, we can plug in. So we're given 7 plus 9. And this is 16. So then it's 4 times 4, which is 16. Okay. So no questions. That's good. Right. Average velocity from 2 to time t. I think what I would want to do first is sort of see what the timeline is. So we start at time t is 2, then we go to time t. This is why I don't like this variable, but time equals t, time equals 2 to time equals t. The average velocity, I'll call that v average. So you want to write down the expression. That's like the change in the distance divided by the change in time. So you've got s of t, because that's the very last time, minus s of 2 over t minus 2. So this will give you the average velocity. And then you should simplify this, actually plug some things in. So then you get t squared minus 4 divided by t minus 2. And hopefully you can see right away how you simplify this even further. So someone tell me. What does this equal? Or you could just type it in chat.
T2.
T. You said something. It was close. T plus 2. Right. So.
Where did you get t squared from?
T squared. I'm using the function. Where did my mouse go? Okay, there it is. So yeah, I'm using this function definition, right? So we're given that s of t is equal to t squared. So I'm just plugging in, and that gives me this t squared. I'm just reading off from the definition. And everyone knows that this is a difference of squares, right? So this factorizes as a, maybe I'll write it off to the side just in case. So when you see a difference of squares like this, you should immediately think of its factorization, t minus 2 times t plus 2. And so that's why you know that you should cancel it right away and get this t plus 2 as the expression for the average velocity. I guess the final thing you might want to do is actually put units to this. So the units here are feet per second. So you might call this feet per second. Okay. Now for part B, we want to find the instantaneous velocity. That's very much related to the average velocity. It's just that we end up making these two endpoints approaching one another. So first, I'll write it symbolically. So we have this expression still calculating average velocity, but we want now for the t to approach 2. So we want to get this endpoint and send it to the left. All right. That's a limit. Limit as t goes to 2. And I can copy down that expression. Okay. And then we would be redoing the work. So let's just use the work that we already found. We know that this fraction simplifies to t plus 2. So we end up getting a limit as t goes to 2 of the expression t plus 2. And now we can just plug it right in. And that gives us 4. And put down the units. Okay. Okay. So, I hope I didn't cover the other pages too much. Oh, no. No, we did. Make all of the pages large first. 6 and 7. Right. So very similar type of problem. We're going from 1 second to t seconds, and average velocity is going to be s of t minus s of 1 over t minus 1. And now we use the function that is given to us, 1 over t minus 1 over t minus 1. And we know that we're going to want to simplify this in order to take the limit for part B. So I guess the best or the easiest way to think about this is if we multiply top and bottom by t, which we can do, right? If I multiply by top and bottom by t, I'm just multiplying by 1. So I'm not changing the function whatsoever. But what this gives us is I can then think of distributing this t over. And what that'll do is cancel out that fraction in a fraction. So we'll end up with 1 minus t over t times t minus 1. Maybe I should have to move these much further. Okay. And do you see that this and this cancel, but they give you back a -1? So that's just a little algebra trick that hopefully you have seen before. So this and this will cancel, but they introduce a negative. Don't know how to denote that, but you get a -1 over t as a result. Put feet per second. Good. And for part B, again, we're going to use this average velocity, but then we let t approach 1 this time. So writing it mathematically, we have to just copy things down. But then we use the work that we did before. And so this fraction simplifies to -1 over t. And then we can just plug in to evaluate the limit, and we get -1. Okay. Any questions? might be very short, so hopefully you have other questions besides the homework. Well, so again, this is so this time around it uses different conventions. So instead we're going from 4 to 4 plus h. That's fine. And so the final time is the 4 plus h. So you have s of 4 plus h. The initial time is 4, so we have s of 4. And then the denominator, if I want to write everything out, I would write 4 plus h minus 4. But that clearly simplifies. Okay, and the numerator, I'm going to plug this. So this is an evaluation, right? We're trying to evaluate s of 4 plus h. So I'm plugging into this function. And this will give me 4 plus h in a square root. And then minus 2 over h. I kind of know ahead of time that to evaluate this thing, I'm going to need to do an algebraic trick. Just to make sure you guys tell me what the algebraic trick is. Am I going too far? Do you follow what I'm saying?
No.
No. Okay. Well, it is in the lectures, but that's fine. So I'll explain. So first of all, let's suppose that we didn't know that. Okay. So we're just going to see what happens when we try to think about the instantaneous velocity. So like before, we have these two endpoints, and we want to get this 4 plus h and make it approach 4. That happens when we let h go to 0. We're taking the limit as h goes to 0. So we get, this is what we want to do to this expression. Let's just put the h. That's fine. Okay. And I'm going to copy down what that expression actually simplifies to. Okay. Now see the problem here. If we try to plug in, we're going to get a 0 over 0. We're going to have a division by 0, and that doesn't tell us anything. So there's a standard technique for this type of problem, because notice that you have this square root and you have like an extra term over here. The technique is multiplying by the conjugate. And I can try to find the slides. I think I have them somewhere. Yeah. So he goes through like these various techniques, and right. Yeah. So starting from this point, this is factorization and cancellation. See how, like, if you were to blindly evaluate, if you would just try to plug 3 into this expression, you would get, you should get 0 on top and 0 on the bottom. You would still have division by 0. That doesn't tell you anything. So you have to, what you have to do is you have to do some algebraic tricks to evaluate these kinds of limits. This section is about the algebraic techniques for evaluating limits. So one approach is factorization. This is an example of doing that. The next one is this expansion. So you're supposed to know how to expand a binomial. You're supposed to, like, that's this guy. And then simplifying fractions is this one. This one's a little bit weirder, I think. Yeah, this one's a little bit weirder. But all you're doing is you're combining the fractions. So the question is, do you know how to combine fractions that have different looking denominators? And the idea is you find a common denominator. Well, it says right there, you find a common denominator, and then from that point, you can then just add the numerators across, putting it over the common denominator. And then hopefully you get some cancellation that lets you evaluate the limit. So finally, you get to this point where you can cancel this x, these x's, and this cancellation lets you evaluate at the end. And the thing that is pertaining to this exercise is this type of problem. You've got like some extra term and you have this square root. So the conjugate is always like this expression, but where you flip the sign. And the reason is actually because of the factorization of difference of squares. I don't have that open. So let me try this out. I haven't used this piece of technology yet, but let me try this out. Oh. There we go. Okay. Yeah. So you see how when you take this and you multiply by the conjugate, what you're doing is you actually end up forcing the middle terms to cancel each other. So that lets you square this term and square this term and give you that as the end result. So no. Yeah. So it's really because it's really coming down. Oh no, it's coming down to x squared minus a squared, x minus a, x plus a. It's really thinking about this in a different way, where what you're given is you're given this guy, and then this guy is your conjugate. And so by multiplying by the conjugate, you end up squaring away the problem. So really, it might be better to have a square root around the x. And then you end up seeing that you square that square root away when you multiply by the conjugate. That's why the conjugate works. And so coming back to our previous problem, try to clear, try to switch. Okay. So the algebraic technique here is multiplying by the conjugate. Well, so first of all, what is the conjugate? Well, it's going to be this, but with the plus instead. So square root of 4 plus h plus 2. And then you can't just multiply out of nowhere. You have to, the only thing you can multiply by is a special version of the number 1. So you have to multiply and divide by the same quantity. Okay. Now doing that, we end up, well, using that trick, difference of squares, we end up squaring away this square root. The middle terms will cancel. We will also square the 2. We'll have a negative. And the denominator is just going to stack on itself. It's just going to be the multiplied across. Like so. Right. And then we can simplify this algebraically. So first of all, the minus 4 and plus 4 will cancel. And then the next thing is you get the h and the division by h to cancel. I'm going to write this over, but normally I would just do both cancellations mentally. It's just that I think that some people mess it up if they try to do both cancellations at the same time. So this cancellation is just because of addition and subtraction. This cancellation is because of division. So when you cancel, you're going to get a 1 on top. Okay. 1 over square root of 4 plus h plus 2. And at this stage, we can now plug in. Okay. This cancellation right here is important because it got rid of that division by 0 that we would have otherwise. So finally, we have something that we could just plug into. And the technical reasons for why I can say that we can just plug into it's because this function is continuous. As I told you earlier, like It's not actually plug into, but it is plug into if the function is continuous. Yeah, you'll just see. It's kind of nice. Okay, so we get that, and then we can say that's 1 over 4. Good, I didn't mess up. Okay. And that's it for the problem set. So are there any questions? Anything else that you want to go over?
Would you scroll back up to 17A?
17A, yeah.
So you kind of just jumped from there to B. Is that what like the final answer would be for that one?
What do you mean I jumped? What do you mean that I could have jumped over?
I just didn't know if you finished with 17A before we went to B.
Oh, I did. Yeah. The only thing that I was saying was like that I could have done the step of this rationalizing or multiplying by the conjugate. I could have multiplied by the conjugate at this stage because I knew that I would need it for this stuff in the future. But no, this is the final part. Oh, one thing I left out units. I forgot units. So all right, let me put units in. Feet per second and feet per second down here. So that's no good if you forget units. Okay. But yeah, no, this is totally valid. Okay. Any other questions? Maybe I wasn't supposed to go through the first half so quickly. Well, we might be ending early a couple of times, just while we're sort of just reviewing the pre-calculus type stuff. I don't know what we can cover next time around. But so, yeah, if you don't have any questions, then we can end here for today. Where will I be posted?
16B real quick.
16, yeah, sure. Let me. Where will I? So someone asked me in chat, where will I post these? So I'm going to post them on YouTube. I have a channel. I'll send an email out.
Okay, thank you.
Okay. There's still a lot of people. Are there questions or? Okay, well, I'm going to stop the recording then. Maybe that's why you guys aren't talking.